Now here we have the following problem. In fact, here the point is that, so we have the problem multiplied already several times. On one hand, we have here q to the h, tensor h, so that's already the same difficulty. But in fact, this difficulty is manageable in the following sense that most of the time these Cartan matrices, they will be diagonalized, they will take some number values, and then you'll be able to sum over these numbers. But the real problem is here, because here we have some real generator, which is, these are the Raising, these are Laurent generators, and they are in degree n, and we have an infinite sum. We have an infinite sum. Of course, if you take a representation in which x plus and x minus are matrices, very soon this power will become 0. So this thing will terminate. It will not be infinite dimensional. But in the abstract way, this is not so well defined. So, and in fact, you may say, yes, but what about the formalism of Jimbo? Unfortunately, this is, as I said, the good thing about the Jimbo formalism is that it doesn't have ill-defined things. On the other hand, the problem is that this thing cannot be defined in his formalism, this factor. You can redefine those, but not this one. So, you see, it is like this in mathematics, that if you push one problem with one side, it will appear somewhere else. So you have to choose what to do. So this was one example of quantum group. In fact, it's called quantum enveloping algebra. Maybe I mentioned this, but let me repeat. Quantum enveloping algebra. Because it was Q deformation of the universal enveloping algebra. And okay, there is another basic, there are two basic examples of quantum groups, which are dual one to the other. And the other one is the so-called matrix quantum groups. I think that I will be able to say how they are really related. I have to say something here, but let me do it a little later. Let me do it a little later. So I will introduce this first in a formal way, and then I will say how to obtain it. So a matrix quantum group is when you have a range for a reason which will become later. You take 4 elements, A, B, C, D. These are generating elements, which you may arrange in a matrix, and I will explain why they can be arranged as a matrix. But first let me mention what relations they have. So these are not ordinary numbers, these are operators, which can be seen in the fact that if they were numbers, of course, two numbers would obey this equality, because for numbers it doesn't matter which one we write first. But here we have if you change the order, appears the number q. It will be the same q I will use over there, and you shall see why. So, okay. And then there is another such relation. And in fact, I'll explain to you the logic of these relations now. Oh, sorry, of course, sorry, of course. Yeah, they always include the same thing. Thank you very much. So why I write it this way is that if I take two which are next to each other, so I write first, and the order they appear, I write AB and then Q, the opposite order. Then I take the second line, CD equal to QC, and then also from the rows, AC is QCA and BD is QVA. Now therefore, remember, there should be two more relations. One relation is simple, namely BC is equal to CB. So there are at least two, which this is commute. So this is the notion of commutation for algebraic objects, not the Lie bracket. And finally, there is one more which is more complicated. It is for AD, and this I write in this way. I write the difference between the two, and this is equal to, I'll call this lambda BC, and lambda will be Q minus 1. So, of course, first of all, you see that this is the formation of an ordinary matrix in the following sense. If I put Q equal to 1, all this becomes commutative like this. Also, this becomes commutative because lambda is going to be 0 if Q is equal to 1. And again, AD will be equal to DA. Now, as you know, matrices have determinants, and the usual determinant of such matrix, let me call this matrix M. The usual determinant is AD minus BC, which means the main diagonal minus the other diagonal. Here, however, we have a Q. So this will be the Q determinant, AD minus QBC. And in fact, if we use, for instance, these relations, you can also write this in the accompanying way. Minus Q minus 1 BC. In fact, this equation is this equation we used in order to write, and both are equal to this Q commutation. Now, how to justify this? How to justify this notation? We actually start with something more simpler. We start with something which we call quantum plane. Quantum plane. Now the quantum plane, since it is a plane, it obviously has two coordinates, which we write as x1, x2. And I want to use a non-commutative quantum plane, so coordinates which will not commute. So I say that these coordinates commute in the following way. If I interchange them, I obtain this Q. And now there is something which I do not cannot explain because maybe you don't know what is Grassmannian, but there is a second quantum plane which I'll call Grassmannian quantum plane. And so this time I will use the coordinates xi1 and xi2, and they will commute in the following way: xi1, xi2 will be equal to minus q to minus 1 of xi2, xi1. And they are called Grassmannian because their square is 0. This is actually the point of being Grassmannian.